Okay, this is Chapter 16, The Fundamentals of Light. I'm not going to read every slide, every word on every slide. I'll leave them up briefly so you could take a look at them. But I just want to get to a point where I can focus on the problems and hopefully keep this to 15 minutes. So, we're going to look at illumination in this video. So we're going to look at this idea of a ray model of light. That's what we're going to be focusing on today. We're going to look at how distance and illumination are related. We're going to come up with a formula for that. And we'll look at the speed of light. So we got a luminous source. That's basically where light's coming from. The idea of opaque means light can't go through it. Translucent, which means some light can go through it. Transparent means that it's relatively clear, we could see through it. Luminous flux is the measurement of the energy coming off the light bulb. Luminance is the amount of light getting to a surface that we're interested in, like for instance our desk. Don't forget, you could stop this video if you need to read what you need to read. Okay, we really can't see light, a beam of light. We can only see it when it's reflecting off of like dust particles in the air or something like that. Okay, so Newton was the first one really to, when he was imagining light, he was imagining unimaginably small particles he called corpuscles, fast moving. What do we call those today? Answer, photons. Okay, but his model kind of fell short. Couldn't explain all the properties of light. Quite honestly, no one model can show all the properties of light. So we actually have a couple of different ways we look at it. Look at it particles, we look at it waves. One thing that kind of ties the two together is this idea of a ray model. Again, all these models are simply ways we come up to think about light. Light is light. All of our models simply represent light. They aren't light. So no model is going to be perfect. So for instance, we think about it as a ray. If it hits a mirror, it reflects off. If it goes through something, an obstruction, it gets refracted. Again, we have artificial means of light. Again, if we wanted to look at, for instance, the difference between sunlight and moonlight, well, sunlight comes from the original source. Moonlight is reflected. So we say that the sun is the luminous source, and we say that the moon is the illuminated source. In other words, we see it because light's reflecting off of it. So again, with our lights, an incandescent light actually produces light. A bicycle reflector just collects light and reflects it back. When you come up behind it and your headlights hit somebody riding a bike, and their reflector on their bike, it almost looks like it's lighting up and illuminating light. It's actually simply reflecting light back at you. Again, when we talk about this idea of transmitted light, we're talking about light passing through. Something that's opaque does not transmit light, does not allow any light to go through. If light can go through, for instance air, glass, that kind of stuff, we say it's transparent. And then there's kind of someplace in between, which is translucent. Means that not all the light gets through clearly, but some of the light gets through. Lampshades, frosted light bulbs, those bricks that they make, those glass bricks that they make showers out of, all are translucent. You could see something through them. There's obviously something on the other side, but you can't see through clearly. Now some things that are will transmit light, like a window, will also reflect some back. That way you could see your reflection in a mirror sometime, in a window sometimes. Okay, so we're going to talk about the energy of light coming off of the original luminous source. We're going to call that stuff luminous flux, and we're going to use the value P to represent luminous flux. We measure it in something called lumens. And so, for instance, a regular 100 watt light bulb might emit 1,750 lumens right at the tungsten filament. And so the luminous flux then is a measurement of the rate at which the light rays come out of the source. Now, if we wanted to figure out, how much light we're getting there, the luminous flux is the maximum amount of light coming right off the source. What we normally measure it at is 1 meter away. But keep in mind that the light is going in all directions. So only a part of it will hit any particular square meter. So we're going to take that 1,750 and divide it by how many square meters we have on the inside. And it affects all of the sphere. Again, if the sphere was larger, 2 meters, once again it would reduce the amount of light getting to any particular section of the inside of the sphere. You can think of it as paint. If I have a certain minimum amount of paint and I have a balloon that's 1 meter big and I paint it with that paint, the paint will be a certain thickness. If I blow the balloon up to be twice as big, then paint it, obviously the paint's going to be thinner. We could think of that as the amount of energy getting to any particular area. So we call that luminance. And again, the luminance goes down as we move away from the light source. I'm going to measure the luminance in something called a lux. A lux is lumens per square meter. And so if we want to figure out how many lumens per square meter or how many lux we get, we have to figure out how far we are away. We're going to use a formula of E is equal to the P over 4 pi r squared. We know that the surface area of a sphere is 4 pi r squared. So if we take our 1 meter, 1 squared is still 1. So 1 times 4 pi, we're going to leave it in terms of pi, and we get 4 pi meters squared. Since that amount of luminous flux is fixed, it's 1,750. We have to divvy that up amongst the 4 pi meters squared on the inside. We get 139 luxes. So a distance of 1 meter, we have 139 lumen meters striking each square meter. So therefore we say that the luminance on the inside of the sphere is 139 lux. Again, if it was larger, you have to keep in mind that your formula, if we have pi r squared on the bottom, if r is 2, 2 squared is 4, 4 times 4 pi is 16, and now we have 16 pi meters squared. Same amount of lux, lumens to become off at that luminous flux, but now it's divided up into an area that's 16 pi instead of 4 pi. In other words, doubling the distance from the light source makes the surface area 4 times bigger. Not just doubled, but 4 times bigger. So the lux goes down to about 35 lux, 34.8. So we say that the luminance at 2 meters is 1/4 of luminance at 1 meter. If we went out to 3 meters, again, it would be, the area would be 9 times 4 pi, which would be 36 pi, so it would be bigger still. So we're going to use this idea of the inverse square relationship. Is the only number that changes in our formula is the radius, and since the radius is in the denominator and the radius is being squared, we're going to call that an inverse square relationship. Sometimes we refer to the luminous source, are talked about in numbers of candela. Candela is not a measurement of luminous flux, it's actually a measurement of luminous intensity. So if it's luminous intensity, it has to be at some distance. The distance they chose, of course, is 1 meter. So basically, when we talk about candelas, we're talking about what the luminous intensity is at 1 meter away. So if we had our 100-watt light bulb, we could say it has 1,750 amount of luminous flux. We would say that the intensity then would be 139 candelas, or 139 lumens per square meter. Again, if we wanted to think about it in terms of, we have a candle on one side casting a certain amount of light on a screen. We have a lamp twice as far away, too deep, twice as far away on the other side of the screen, casting the same amount of light. How bright does the lamp have to be in relationship to the candle? Well, it can't just be twice as bright, it has to be 4 times as bright. So let's take a look at a problem where we're going to try to light up a desktop. So if we wanted to light up our desktop, we could use a brighter light, or we could move the light source closer. We're going to do a problem. We're going to keep everything in terms of a point source. I'll talk a little more about this in class. We're going to talk about our inverse square relationship. We're also going to assume that the light is striking the surface perpendicular, which makes, again, life a little bit easier. And so here's our equation. E, which is the luminance, is equal to P, which is the luminous flux at the source, over 4 pi r squared. So if we know what the radius is and we know what the P value is, we could figure out the new E value at any particular distance. Again, the luminous flux is traveling out in all directions, so you're only going to get a fraction of the luminous flux at any particular area. So there's a couple of caveats in here on when it's valid and when it's not. So let's take a look at a problem. Let's say we have a desktop and it's lit by a 100-watt light bulb or a 1,750 lumen lamp, and that light bulb or lamp is 2.5 meters away from your desk. Sketch the problem out, and the desk actually should be perpendicular. It's not, but you could see our P value then is 1,750 lumens, or 1.75 times 10 to the third lumens in scientific notation. Radius, make sure you put your radius in meters. It already is in this problem at 2.5. So we know what our P value is, we know what our R is. We're solving for E. We just need an equation. And we know that E is equal to P over 4 pi r squared. Substituting in our values, we could then do the math. And we get 22.3 lumens per meter squared. We could also say 22.3 lux. Lux is lumens per meter squared. Can't say candelas because candelas is only good for 1 meter away. So we want to look at it, make sure our units are correct, and it is, and do the signs agree, and they do. Is it realistic? Yep, it's smaller than when we had 2 meters earlier on when we calculated that. We'll get to do some math problems in class. So again, this is something that engineers would be interested in. So the speed of light. Galileo was really the first one to say that the light has a speed, that it wasn't infinite. That when we turn a light bulb on or we flip a switch, the light is instantaneously every place in the room all at once. Actually, it is. If we were able to see fast enough, we would actually see the light start to dissipate the darkness as it moved out, but it moves so fast that we can't determine it. Galileo, though had an idea that it did have a speed. He tried to measure it, but it was just too fast for anything that he could measure it with. So really the first guy that came up with any kind of measurement was a guy by the Romer, by game of Romer. And what he was doing was he was noticing that if you measured how long it took the moon of Jupiter, Io, to pass behind Jupiter, it was longer at some times of the year than others. And he attributed that to the fact that the Earth is moving around the Sun, and sometimes the Earth is moving away from Jupiter in relationship on its axis compared to Jupiter, and sometimes it's moving towards Jupiter. If we're moving away from Jupiter, it's going to have one speed. Towards Jupiter, it's going to have a shorter speed. And he attributed that to the fact that that the light bouncing off of the moon and getting back has something to do with it. So he came up with some predictions, and what he figured out was, again, as we're passing, going away from Jupiter, it takes 13 seconds longer for Io to show up. When we're moving towards Jupiter, it's 13 seconds shorter, and he attributed this to the speed of light and our speed. Came up with the idea that all in all, then, that light takes about 22 minutes to cross pass through our orbit, based on how fast the speed shows up going one direction than the other. Did some calculations and figured out that it takes about 22 minutes for light to travel the diameter of Earth's orbit. From that, he was able to calculate the speed of light, and he came up with 2.2 times 10 to the 8th meters per second. Not too bad. I mean, it sounds like it's a little bit off. We know it's 3.0 times 10 to the 8th, but he got the 10 to the 8th right. He got the order of magnitude right. Not too bad for the equipment that he was working with at the time. We also know that it actually takes light 16.5 minutes, not 22 minutes, to cross the Earth's orbit. But like I said, considering what he had to work with at the time, not too bad. Another guy was looking at this. Michelson is more famous for it, working between 1880 and 1920. He developed a method on Earth to measure the speed of light. He actually had two labs set up 35 kilometers apart on two California mountains. He used a set of rotating mirrors, and so he was able to measure very small time intervals, and he was actually able to get the speed of light down to the number that you see there on the screen, and he won a Nobel Prize for that. And so, of course, today we know that the speed of light in a vacuum is 299,792,458. Again, we always round it to 3.0 times 10 to the 8th power. And again, we could look at how long it takes to travel in a year. That's a light year. Remember, a light year is a distance and not a time.